Hello once again. So we're now on application of first order differential equation. So this time, we'll be uh, discussing or solving problems or solving mixture problems. Okay, so using methods of solution for first order differential equation. So when we say mixture, so we're talking about a solution. Okay? So or it's a combination or a mixing up a solution with another solution. But when we say solution, so this is a combination of a solute and a solvent. Like for example, we have a coffee. A coffee is a solution of water. Okay, so as the solvent, and then the coffee itself plus the sugar. Okay, so could serve as the solute. Okay, so in the given mixture. So another common solution as well would be the brine solution. So which is a combination or of a salt and water. And for every given solution, we can solve, okay, or we can find the amount of the solute or the amount of the substance at any instant of time. And the governing differential equation on how to find, okay, so the amount of the substance at any instant of time. So whenever, let's say, we have a solution inside the tank, and then another solution is being poured inside the tank, so the amount of or the rate at which the amount of the substance, okay, so changes over a period of time is equal to the concentration, okay, or the input concentration of the solution, so being poured in, so multiply it for the volumetric flow rate, and then subtracting the output flow rate, multiply it with the output concentration. So in this given figure, so we can see here, or we can define different variables, so which is given in the said mixture. Okay, so let's say we start with this. We start with the solution. Okay, so inside the tank. So X here, so correspond to the amount of solute, okay, or the amount of the substance inside the tank. So usually we express the amount of the substance in terms of mass. Okay, so we can express it, let's say in kilogram. It could be in pound mass. Okay, so that's how we express the solute or the amount of the substance inside the tank. And then we have the variable V. Okay, so V here is another variable, so which designates the volume of the solution. Okay, so the volume of the solution inside the tank, so corresponds for V. Okay, so this is not the volume of the tank, but rather it is the volume inside the tank, okay, or the volume of the solution inside the tank. So that's our first solution. So another solution, okay, so would be this one. Okay, so the solution that is entering the tank. Okay, so the solution that is entering the tank is described in two parameters. So first, we have the input concentration, and then we have the input flow rate as well. So when we say input concentration, so that is the amount of solute per unit volume. Okay, so that's the amount of solute per unit volume. So let's say we are given a brine solution, so which is entering the tank. The concentration, so would be the amount of salt that is present for every unit volume. So let's say it would be equal to 2 kilograms per gallon, okay, per gallon of the given mixture, okay, or of the given solution. So that is how we measure the concentration. So concentration is the same as the density, okay, so in a general sense. So this would be the mass per unit volume. Okay, so that's the amount of the solute or the amount of the substance per unit volume. When we say QI, so QI is the volumetric flow rate. So how fast is the solution entering the tank? Okay, so QI is how fast the solution is entering the tank. And another thing that we need to take a look at the given figure, so would be our C out and Q out. So Q out, of course, would correspond to the output flow rate. Okay, so corresponds to the output flow rate, and then we have the output concentration as well. But take note, okay, so for the output concentration, so although this is a solution, okay, so which is going out, okay, so which is going out from the tank, but take note that the solution that is going out is the solution that is inside the tank. So therefore, the concentration, okay, so the concentration inside the tank is the same as the output concentration. So it's because the solution that is going out from the tank is the solution that is from the tank. Okay. So out of the different parameters here, so we have to take note that the amount of solute inside the tank varies. Okay, so this one varies. So depending on what would be the solution that is entering the tank. So the volume varies as well, especially if the input flow rate is different from the output flow rate. Okay? So the volume of the solution so varies as well as time goes on. But most of the time, okay, so most of the time, the input concentration is fixed. Okay, so the input concentration is fixed unless otherwise the input concentration was, or the equation for the input concentration was provided. But if not, okay, so most of the time the input concentration is constant. So for QI, it's constant. Okay, so unless otherwise, so the equation is provided. So similar with the Q out. But then for the output concentration changes. Okay, so because the concentration depends on the amount of the solute per unit volume. So therefore, if the flow rate is different, okay, so if the flow rate is different, and at the same time the concentration of the solution going in and the solution inside the tank are different, so definitely the concentration in the tank after some time will change as well. So whether it will increase the amount of solute or whether it will decrease the amount of solute. So depending on the problem. So next, we have the concentration. So again, so the output concentration is similar to the concentration inside the tank. And the concentration, as I've mentioned, is similar to density, so which is mass per unit volume. So in this case, so X corresponds to the mass or the amount of the solute inside the tank. So divide it with the volume. Okay, so the volume of the solution inside the tank as well. But then the volume of the solution varies, okay, over a certain period of time. So it changes. So initially, okay, so it is equal to the initial volume of the solution inside the tank. But it varies because the input, okay, so the input flow rate and the output flow rate varies. Okay, so there are three things that could possibly happen for our flow rate. Okay, so when the input is greater than the output, okay, so when the input flow rate is greater than the output flow rate, so that means if the input is greater than the output, so this term, the QI minus Q out, okay, so the QI minus Q out, so if QI minus Q out, or if QI is greater than Q out, okay, so the input, so minus the Q out, okay, so will be greater than 0. Okay, so that means if the input, okay, so if the input flow rate is faster, okay, as compared to the output flow rate, okay, so QI minus Q out becomes more positive. Okay, so QI minus Q out will be greater than 0. And thus, after some time, okay, so what happens to the volume? So the volume increases. The volume increases, and then at time is equals to infinity, so the volume, okay, or the solution, okay, so the solution overflows. Right? So because we have a finite, okay, so we have a finite tank, okay? So that after some time, after many time, okay, so the solution will overflow. So since the volume of the solution increases. The second one is when the input flow rate is equals to the output flow rate. So therefore, the Qi minus Q out, so since both are equal, so it will become 0. So therefore, the volume, okay, so inside the tank is actually equal to the input volume, okay, or the initial volume. So the initial volume is constant, so it doesn't vary anymore. Although there would be a flow of the solution inside, going from inside the tank to outside of the tank, but then the volume of the solution inside the tank is fixed, so which is equal to the initial volume. And lastly, so when Qi, or the input flow rate, is less than the output flow rate, okay, so the input flow rate is less than the output flow rate, so Qi minus Q out becomes more negative, okay, so it becomes less than 0, and thus V decreases, and when time is equals to infinity, so the solution becomes 0. Okay, so we empty the tank, okay, so after a very long time. Okay, so those are the three things that could possibly happen within the given tank. Okay, so but take note that the volume inside the tank varies, the amount of the solution or solute inside the tank varies as well. So if the amount or X varies and the volume varies, so it follows that the output concentration is not constant, it varies as well. So let's have our first example. So we usually visualize it through a representation of a tank. Okay, so let's say we are given a tank. Okay, so and then we represent the amount of the solution that is going in and the solution that is going out as well. So initially, it says that a tank initially holds 100 gallon of brine solution, so containing 20 pounds of salt. So initially, there's a solution inside the tank. Okay, so there's a solution inside the tank, and the volume of the solution is 100 gallons. So therefore, initially, so there would be 100 gallons of brine solution inside the tank. And out of the 100 gallons of solution, so it contains 20 pounds of salt. So that means the amount of solute, which is X sub O, so that is 20 pound. Okay, so 20 pound of salt. But then at time is equals to 0, okay, so initially again, so fresh water is poured into the tank at the rate of 5 gallons per minute. So 5 gallons per minute. So that is a volumetric flow rate. So therefore, that will be Qi. So the input flow rate, so it is 5 gallons per minute. So if there is a Qi, or the flow rate, so we need to know, so what will be our input flow rate, Ci. So when we say concentration, so this is a just so happened that what is entering the tank is not a solution. Okay, so rather it's a fresh water. So when we say fresh water, so that is just purely water. So there is no substance within the water. Okay, so there is no solute. Okay, so for the given for the fresh water, so therefore this is not concentrated. Okay, so this is not concentrated, and it follows that the concentration will be 0. Okay, so no amount of solute, okay, so present in pure water. Okay, so therefore the input concentration will be 0. And then while the well-stirred mixture leaves the tank at the same rate, so that means the output flow rate is the same as the input flow rate, so which is 5 gallons per minute. So 5 gallons per minute. So we have a statement there that it says that it is well-stirred mixture. Okay, so for every mixture problem, so it is our assumption. Okay, so it is our assumption that the solution inside the tank is well mixed. Okay, so that means the substance, okay, so is equally distributed on all parts of the solution. So that means for every part of the solution, there's an equal amount of solute. Okay, because if you're not going to mix it, okay, so there's a possibility that the solute, okay, so will settle down at the bottom of the tank. Okay, so thus we cannot accurately measure so how how the solute, okay, so behaves, or how the solute changes over a certain period of time. So that's why most of the time you will see, okay, so this is statement on every mixture problem that it is a well-stirred mixture. And then we have the output concentration, which we do not know because it varies. So looking at the example, so it says that we have initially 20 pounds of salt inside the tank, but then there's a fresh water that is going in, okay, so inside the tank, so without any salt content, okay, so on that solution. So therefore, if there is a continuous flow of fresh water inside the tank, so it will dilute the salt, okay, so inside the tank. That after some time, okay, so this salt, okay, so will be reduced in its amount, okay, so because it will be flashed out, and the fresh water, okay, so will dilute this one. So that is how we draw our given. So to visualize it, so how it works, or how the solution behaves. So for our requirement, so since we already have an analysis of the given problem, that after some time, so since pure water is entering the tank, so the salt will be reduced. Okay? So the amount of salt inside the tank will be reduced. But the question now is, so if the salt pertains to X, so after 10 minutes, so how many pounds of salt are there inside the tank? How many pounds of salt are there inside the tank? So to resolve this one, so since we are to find the amount of salt, so we have our formula, so which is the differential equation. So dx over dt is equals to Ci Qi minus C out Q out. So dx over dt will be equal to, our input concentration is 0. Our input flow rate would be 5 gallons per minute. Our output concentration is unknown, but then our output flow rate is 5 gallons per minute as well. So dx over dt then, so this one will be 0, so leaving us to have a negative 5 times C sub O. But we have formula for C sub O. Okay, so the output concentration is the same as negative 5, so which is X all over initial volume plus Qi minus Q out times time. So now we substitute. So again, so the amount of salt is variable. So we do not substitute the given right away. So for variables, okay, so for dependent and independent variable. In this case, that is x and t. So negative 5, so multiply it with x, so which is a variable. So initial volume is not variable. So it's already given that initially there are 100 gallons. So we substitute 100. Our input flow rate is fixed, constant at 5 gallons per minute. So similar with the output, which is 5 gallons per minute as well. But of course, time will be variable. So thus 5 minus 5 will be 0, eliminating it. Okay, so next we have dx over dt, so will be equal to, So negative 5x all over 100, so we can reduce it to its lowest term. So by dividing it by 1 over 5, okay, so for the numerator and denominator. So giving us a negative x all over 20. And now, so giving us, okay, so giving us the differential equation. Okay, so giving us the differential equation. So dx over dt is equals to negative x all over 20. And the kind of differential equation, okay, so this one is a separable equation. Okay, so we can easily solve this one so by separating x from t. So moving x to the left-hand side of the equation, so that would give us dx over dt. And then dt to the right-hand side of the equation, so that will be negative dt all over 20. So and now we can find the solution. Sorry, dx over x. Okay, so dx over x is equals to negative dt over 20. So dx over x is ln x. And dt over 20, so that's the same as negative t all over 20. So we just move out the constant, which is negative 1 over 20. So the integral of dt is just t. So multiply it with negative 1 over 20, so which is equal to negative t all over 20. Then of course, plus the arbitrary constant c. And next we find or we express x explicitly in terms of t. So we exponentiate both sides. So exponentiating both sides, so that will give us x will be equal to e raised to negative t all over 20, then multiply it with e raised to c. Or x would be simply ce negative t all over 20. So now we have our equation as x versus time, but then we have the arbitrary constant c. So we need our initial value. So when t is equals to 0, so we need to determine what is x. Okay? So how much of salt is around at times equals to 0. And we can get this one here. So at times equals to 0 initially, so there is 20 pounds of salt. So that is why we substitute. So x will be 20. So substituting x to be 20, so 20 is equals to ce negative 0 over 20. So e raised to 0, so will be 1. So therefore, c is 20. And our final working equation for x then, so will be 20 e raised to negative t all over 20. So this is the working equation, so for x. So for every value of t, so what happens to the value of x? In this case, we are tasked to find, so when t is 10 minutes, so what should be the value of x? So in this case, that is x, so 20, e raised to negative t is 10, divided with 20. And finally, the amount of salt, okay, so that is present after 10 minutes is approximately 12.13 pounds. So 12.13 pounds of salt. Okay. So approximately 7. Okay. So 7.83 pounds wash out was washed out. Okay. So from the mixture or from the solution inside the tank. Okay. So we just need to understand how the solute behaves inside the tank, and then from there, so we have a clear understanding so what is really happening in the given mixture. Okay, so that's our first example. So let's have our second example. So again, most of our or all of our problems pertaining to brine solution. Okay, so to just make it simpler, okay, so But then there are different applications in the field of engineering. Okay? So let's say if you are civil engineering, so you can have a mixture of a cement, okay, and any other materials that you have in construction. So for mechanical engineering, so you have your different chemicals. So in the laboratory, so that you can mix up. So in this case, we are just simplifying. Okay, so our examples. Okay, so to better understand how solution behaves over a certain period of time. So let's say we have again a tank. So this time around, so we have a 50-gallon tank. Initially contains 10 gallons of fresh water. Okay, so we have two volumes here, 50 gallons for the tank and then 10 gallons of fresh water. So the initial content of the tank is not a solution, but rather it's just the solvent, so which is a fresh water. So that means that is what is inside. So the initial volume of the solvent there, so which is fresh water, that is 10 gallons. And then, since this is fresh water, so initially, so there is no solute inside. Okay? So if there's no solute inside, so because it is fresh water, so therefore that would make it 0. And then we have the 50-gallon tank. So that means that's the capacity. Okay? So the capacity of the tank. So the capacity of tank is 50 gallons. So initially, a brine solution is containing 1 pound of salt. Okay. So for this example, fresh water is inside the tank and a brine solution is entering. In opposition to our first problem that we have a brine solution inside the tank and then a brine or a fresh water is entering. Okay, so this is the other way around. So in this case, we have a solution or a brine solution. So it contains the concentration of 1 pound per gallon. So which enters the tank at an input flow rate of 4 gallons per minute. It is well stirred mixture and then it leaves the tank at the rate of, so Q out is 2 gallons per minute. Okay. So QI is greater than Q out. So that means at some time, okay, after some time, so since QI is greater than Q out, it will overflow. So the question now is, so what would be the amount of time required for overflow to occur? So when will it overflow? Okay. So in this case, so what would be that time when it will overflow? So it will overflow when the volume exceeded the capacity, or the volume of the solution exceeded the capacity of the tank. So in this case, the capacity of the tank is 50 gallons. So when the volume is greater than 50 gallons, okay, so when the volume is greater than 50 gallons, so that is the time that the overflow will start to occur. Okay. For the second one is, what would be the amount of salt in the tank at the moment of overflow? So when it is about to overflow, so what will be the amount of salt? So the amount of salt is X. So what will be the volume right at the moment of overflow? So it will overflow when V is equal to 50 gallons. Okay, so that's the difference. Okay, so for the first question, so what would be the time required? So to overflow. But then, when it is about to overflow, okay, so what would be the amount of salt? Okay, so for our solution, the first requirement is time. Okay, so time is required, and then we have the volume, so which is 50 gallons. So 50 gallons. So we have two set of formula in mixture. So one is the dx over dt, so the differential equation, which is usually used when we are given with time, and then we are finding the x amount of solute. But then in this case, what is given is the volume. Okay, so volume which is greater than 50 gallons, and then we are to find the time. So we cannot use the dx over dt formula. So since that's the relation between the amount of salt or the amount of the substance versus time. But then we have a formula for the volume. Okay, so that is when V is greater than 50, so what is time? So our formula is V is equals to the initial volume plus the input flow rate minus output flow rate, multiply it with time. And then so we transpose initial volume is equals to Qi minus Qout times time. So T then will be equal to volume, okay, so the volume at any time, so minus the initial volume divided with Qi minus Qout. So now we can substitute. So the volume when it is about to overflow is 50 gallons. So that is the volume of the tank. So initial volume is 10 gallons. The input flow rate is 4. The output flow rate is 2. So T then will be 50 minus 10 is 40. So divide it with 4 minus 2, which is 2. So 40 divides 2, that is around 20 minutes. So therefore, when will it overflow? So at 20 minutes, okay, at exactly 20 minutes, so it will reach the capacity. Okay, so it will reach the capacity of the tank. So therefore, it will overflow when time is greater than 20 minutes. So when the time is greater than 20 minutes, so that is the time that it will overflow. For the second requirement, so what would be the amount of salt, okay, when it is about to overflow? So when the volume is exactly at 50 gallons, so what will be the value of x? So again, the value of x is dependent to time. Okay, but then we already have the time. So when it is about about to overflow, so it will exactly it will about to overflow when time is 20 minutes. So therefore, we just need to develop our equation, okay, so for x, so versus time, and that is when V is equals to 50 gallons, so it follows that the time is equals to 20. So therefore, what will be the value of x? And we have our working equation that dx over dt is equals to Ci Qi minus Cout Qout. And dx over dt, so we substitute right away the formula for Cout, so which is x all over initial volume plus Qi minus Qout times time, then multiply it with Qout. So dx over dt, our input flow rate is 1 or 4, concentration is 1, output is 2. So input flow rate is 1, so Qi is 4 minus x all over initial volume is 200 plus input flow rate is 4, output is 2, output flow rate is 2. So dx over dt then is equal to 4 minus 2 times x is 2x all over 200 plus 2 times t. So we have 2x, and then we can factor out 2 at the denominator. Or sorry, it's not 200. So it's just 10, okay? So the initial volume is just 10 gallons, sorry. So 10 gallons. So that makes it 2, then 5. Or we factor out 2, and that would become 5 plus t. And we can see here that we can factor out 2. And thus, giving us dx over dt is equals to 4 minus x all over 5 plus t. So I can rearrange this one. Okay, so transposing x to the left hand side, so it will become plus x, and then 1 over, so I'm going to interchange 5 and t, so t plus 5, so will be equal to 4. So this is the same as dx over dt plus 1 over t plus 5 times x is equals to 4. And as you can see here, so the equation that was developed was a linear equation. So citing that our p of t is equal to 1 over t plus 5, and then our q of t is equals to 4. So now we use the formula. Okay, so in finding the integrating factor, so that is e raised to, so dt all over t plus 5, that is equals to e raised to, so our pt is 1 over t plus 5. So therefore, we can right away find the solution of these as ln or ln of t plus 5, and then applying properties of logarithm. So finally, our mu of t will be t plus 5. And since our working equation then, so would be mu of t, so multiplied with linear in x, then q of t, mu of t, dt. So our mu of t is t plus 5, then our x is equals to, q of t is 4, mu of t is t plus 5 dt. So in here, so we can use power rule, so to integrate this. So u is t plus 5, so du will be dt. So thus we can use, so t plus 5 times x is equals to, so 4. So power rule is t plus 5 raised to 2 all over 2 plus c. So t plus 5 times x will be equal to 2 times t plus 5 squared plus c. And then if we want this one to work explicitly, so we can divide everything by t plus 5. So giving us x, 2 times t plus 5, then plus c all over t plus 5. And thus when t is equals to, what's that? So when t is 20 minutes, that is the time that it will overflow. Okay, so what will be the amount of x? So x then will be 2 times 20 plus 5, so which is 25 times 2, which is 50. Or we cannot right away find this one, so we need to find the value of c first. That is when time is equals to 0. Okay, so it states that x is 0 as well. So because when time is equals to 0, so in here, so the amount of salt is 0 as well. So we need to find what's the value of c first. Okay, so x is 0. Okay, then 2 times 5, then plus c all over t plus 5. So this would, c will be, or t is 0 as well, or t is 0, so therefore we'll have 5 there. And then this one would make it, so 2 times 5 will be 10. So then transpose it, so negative 10 is equals to c plus 5. So therefore, c is equal to negative 50. And thus, so we have x is equals to 2 times t plus 5 minus 50 all over t plus 5. And this time, so when t is 20, so what would be the value of x? So x then will be 2 times 20 plus 5, then minus 50 all over 20 plus 5. So 20 plus 5 is 50 times 2, or 20 plus 5 is 25, times 2 is 50, minus 50 over 25 is 2. So therefore, we have 48 pounds. Okay, so for our so we have 48 pounds of uh, salt. Okay, so for the given mixture. Okay, so let's have our last example. So we have a similar mixture. So again, it's a brine solution. So we're in initially, a tank contains 200 liters of fresh water. So it's fresh water again. So initially, so that would be 200 liters. And then since it is a fresh water, so the amount is 0. So brine containing 2.5 newtons per liter, dissolved salt runs into the tank. So the concentration would be 2.5 newtons per liter. And then the rate of input, so QI is 8 liters per minute. The mixture is kept uniform by stirring runs out at 4 liters per minute. Okay, so Q out is 4 liters per minute. So find the amount of salt. So which is measured in terms of Newton. Okay, so although Newton is force, right? So 2.5, or sorry, find the amount of salt when the tank contains 240 liters of brine. So what is X? So when V is 240 liters. So initially it's 200 liters. Okay, so since the input flow rate is greater than the output flow rate, so the volume increases. So and the amount of salt increases as well. So in this case, so what would be the amount of salt when the volume is 240 liters? And then lastly, so the concentration of salt in the tank after 25 minutes. So the concentration of the tank is the same as the concentration, output concentration. So what would be the concentration when time is 25 minutes? So for our solution, so we start with when V is 240, so what would be X? So we cannot right away, so find the value of X, so using dx over dt. So since X is dependent only with time, so we need to find the time first. Okay, so from the previous example, okay, so we were able to compute for time as the volume, so minus the initial volume over Qi minus Q out. So the time it would take, so to reach the solution to 240 liters, that would be 240 minus the initial of 200 divided with Qi, so which is 8 minus 4, so for our Q out. So time then would be 40 divided with 4, so that is approximately 10 minutes. So this time, so when the volume is 240 liters, so it would take 10 minutes to do it. Okay? So, or to increase the volume to 240 liters. So now we compute for the formula dx over dt. So Ci Qi minus C out Q out. So dx over dt. So Ci Qi and C out is x all over initial volume plus Qi minus Q out times T, multiply it with Q out. So dx over dt then, our input concentration is 2.5. Then we have 8. Okay, so for the input flow rate, minus x, which is variable, initial volume is 200. So input is 8 minus 4 for the output times time. Output is 4 as well. So dx over dt, 2.5 times 8 is 20, so minus 4x all over 200, so plus 40. So we can factor out 4 there, so making it so minus 4x all over 4 times 50 plus t. So we cancel out 4 and we transpose it, so it will become plus 1 over t plus 50 times x is equals to 20. So p of t, okay, so this is our p of t, and q of t is 20. So we find the integrating factor. So mu of t would be e raised to the integral of p of t, which is dt all over t plus 50. So it is e raised to ln t plus 50, or just simply t plus 50. So mu of t times x then will be equal to q of t mu of t dt. Mu of t is t plus 50, so times x, so q of t is 20, then t plus 50, so for our mu of t dt. So we use power rule, so giving us so t plus 50 squared over 2, or just simply 10 t plus 50 squared plus c. So we can find for the value of c, so when t is 0, so x is 0 as well. So since that is a fresh water. So giving us so t plus 50, so 0 plus 50 is 50, so times x, which is 0, is equals to 10 times, so 0 plus 50 is 50 squared plus c. So c then will be 50 squared is 25 times 10, it's 25,000. Then transpose it, so we'll have negative 25,000. So finally, our working equation would be t plus 50 times x, so 10 t plus 50 squared, so minus 25,000. So we multiply everything by 1 over t plus 50, so x will be 10, so t plus 50, then minus 25,000 over t plus 50. So this time, so when time is 10 minutes, so that is when the volume is 240 liters. So what is the amount of salt? So x would be 10 times, so 10 plus 50 minus 25,000 over 10 plus 50. So x is 183.33 Newton. So x is 133 Newton. So when the time is 10 minutes. So for our second requirement, so it says that, so what would be the output concentration when the time is 25 minutes? So when time is 25 minutes, so what is the output concentration? So the output concentration formula is x all over the initial volume plus qi minus q out times the time. So we have the initial volume, the input flow rate, and the output flow rate. And then we need to find the value of x. Again, so although we found x to be equal to 183.33, this is not the x that we're going to use. It's because 183.33 Newton is the amount of salt when time is 20, or when the time is 10 minutes. Okay? But in this case, we are to find the output concentration when time is 25. So therefore, we use the formula for x, okay, so which is this one. Okay? So the formula of x, so we substitute, so we develop this, so therefore we substitute it. And then we divide it with this formula. Or I'll just write it. So output concentration is initial plus qi minus q out times time. So the output concentration then So it would be 10. So the time is 25. So 25 plus 50 minus 25,000. So 25 plus 50. Divide it with initial, which is 200, right? So initial volume is 200 liters. And then plus 8 minus 4 times 25. And thus our output concentration is 1.39. So 1.39 newtons per liter. And that is the output concentration, so which is the same as the concentration inside the tank. And that is how we solve mixture problems, so using first order differential equation. And that will be all. Have a great day again, and God bless always.